It's Monday 2 a.m. and your production server just crashed. Out of memory error, client calls, manager calls. You're checking the system now, leaving your coffee untouched. And what do you find? It crashed simply because you didn't manage threads properly. One simple mistake, and this one mistake ruined your entire night. If you write Java concurrency code and you create threads directly, this video is for you because today I'm going to teach you how the Executor framework can save you from that nightmare. Hello everyone and welcome back to the channel. Today we are starting a brand new series, Java Executor Framework Mastery. In this video we are going to learn three important things. First, why raw threads are dangerous, practically risky for production applications. Second, what is this executor framework and how it fixes those problems. And third, I'll show you real code examples of different thread pools. And yes, I'll also demonstrate how to build a custom thread pool that often comes up in the interviews. So get your coffee or tea ready because this video is a bit long, but every minute is packed with value. Let's get started. Imagine you're building a simple system that processes tasks. Tasks could be anything, maybe computing something heavy or processing data. You have a list of tasks and you need to process them one by one. What's the simplest approach? Just do everything in one thread, right? If you have started learning Java, you might have written code like this at some point. Sequential task processor. You iterate or list of tasks and you process each task one by one. This code is theoretically correct, but in practice, this is disaster. Why? Simple reason. It can handle only one request at a time. Suppose a request comes that needs to run a database query, taking 2 seconds. Meanwhile, 10 more requests arise. What happens to them? They have to wait, right? And if that database query takes 10 seconds instead of 2 due to network issues maybe, user will think the server is down. This is the blocking problem. When one thread blocks on I/O, the CPU sits idle, but new requests cannot be processed. So what's the solution? Simple. Create new thread for each request like this, thread per task processor. So for each task we are creating a new thread. Now what happens? Each task run in its own thread. The main thread quickly starts all the threads and then they run concurrently. If you have multiple CPU cores, they actually run in parallel. The total time is now roughly the time of longest task, not the sum of all tasks. Much faster, right? But wait, this approach has some serious problems. Three major drawbacks. Number one, lifecycle overhead. Creating and destroying threads is not free. Each thread requires the OS to allocate resources. When you create a new thread, for every request, a significant amount of CPU time goes just into creating and removing threads, not into actual request processing. Second, memory consumption. Each thread has its own stack. Default stack size is usually around 1 MB. So 1000 threads means 1 GB of memory just for stacks. And this is not heap memory, this is native memory. Your heap contains your objects too, so total memory pressure is much higher. The third drawback is stability. The operating system puts a limit on how many threads you can create. Windows or Linux each has different limits. When you cross that limit, what happens? Out of memory error, unable to create new native thread. And when this error appears, there is usually no chance of recovery. Your application simply crashes, and all this happens just because you didn't put bound on threads. So the message is clear. If you don't limit thread creation, there is no limit on getting calls at 2 a.m. So far, we have understood what the problem is. Now the question is, what's the solution? Does Java have something that manages threads, pools them, and saves us from all these headaches? Yes, absolutely. And that solution is called the Executor Framework. To understand the Executor Framework, we first needs to understand one pattern. This pattern is called producer consumer pattern. It is very simple. Think of a restaurant. You place an order, you are a producer. The waiter takes the order to the kitchen, that is the queue, and the chef who prepare the order, they are the consumer. In this pattern, producer simply creates the order and puts it in the queue. They don't care which chef prepares it or how. The consumer takes order from the queue and process them. Producers and consumers work independently. This same pattern exists inside the executor framework. Look at this executor interface. Look how simple it is. Just one method, execute. You give it a runnable, so it executes it. But how? That depends on your policy. So what is execution policy? An execution policy is simply a set of rules. For example, which thread will run this task? A new thread? An existing worker thread? In what order will tasks run? First in, first out, last in, first out, or priority order? How many tasks can run at the same time? If the queue becomes full, what should happen? Reject, wait, or block? How many tasks can wait in the queue? When you are using raw threads, your policy was fixed. A new thread for every task. You couldn't change it, but with Executor, you can change the policy without changing your task submission code. Change one line and the entire behavior changes. This is decoupling. Task submission is separate from task execution. So the producer code remains the same, but you can change the execution policy. See, the code submitting the task doesn't need to know what policy is being used. It just submits. The executor handles the rest. This is powerful. At deployment time, based on your hardware, you can choose the right policy. If you have 8 cores, use one policy, 32 cores, use another policy without changing your business logic. But wait, how does Java actually implement these different policies? What happens inside those executors static factory methods? Let me show you the inheritance hierarchy first. The family tree of the executor framework. This will help you understand what's really going on under the hood. Let's start from executor interface. This is the simplest interface in the entire framework. Just one method, execute. It says, here is the task, run it somehow. That's it. No lifecycle management, no result handling, no shutdown, just execute. This interface is the foundation. Every executor in Java implements this method. When you call execute, you don't know if the task will run in a new thread or in an existing thread or even in the current thread. That's the beauty of decoupling. Executor service, the parent. Executor service extends the executor interface and adds the things you need to manage the life cycle of the executor. Now you can submit tasks and get a future in return like this to track their progress or get results. Shut down the executor gracefully like this, preventing new tasks from being submitted while allowing existing ones to finish. Wait for termination so you know when all tasks are done. Invoke collections of tasks and wait for all or any to complete. This is the interface most developers work with directly. When you see code like this, you're holding an executor service reference. And this is how you use it to execute task and get future in return. And this is how you can shut down the executor. Now let's go to abstract executor service, the skeleton. Abstract executor service is an abstract class that provides default implementations for most methods in executor service. It handles the boilerplate code for you. So concrete implementations don't have to reinvent the wheel. For example, it implements submit method by wrapping the runnable into a future task and calling execute method. It also provides default behavior for invoke all and invoke any. This class is meant to be extended by the custom executor implementations. You rarely use this class directly, but it's the backbone that makes creating new executors easier. Next is ThreadPool Executor, the workhorse. Now we reach the most important class in the framework, ThreadPool Executor. This is the real engine behind most of the executors you create. When you call executors.newFixedThreadPool, you're actually getting an instance of ThreadPool Executor configured with specific parameters like core pool size, maximum pool size, keep alive time, the type of queue, and the rejection policy, etc. Notice the queue here. I used bounded linked blocking queue with capacity 100. This prevents unbounded growth and protects your application from memory exhaustion. The rejection policy says if the queue is full, all threads are busy, let the caller thread run the task itself. This provides natural back pressure. We'll talk about all these parameters later in this video when we'll build our own custom thread pool executor. Next is scheduled executor service, the timekeeper. Sometimes you need to run tasks after a delay or repeatedly at fixed intervals. That's where scheduled executor service comes in. It extends executor service and adds methods for scheduling. So schedule method runs a task once after a delay. Schedule at fixed rate runs a task repeatedly starting after an initial delay with a fixed period between the start of executions. For example, a task starts at 9, initial delay is 10 minutes, first task runs at 9:10 with a 10-minute fixed rate. Next runs are scheduled for 9.20, 9.30 and 9.40 etc. If first task takes longer, say 20 minutes, the scheduler still tries to start the next one at 9:20. Now the key question here is, does next task starts at 9:20 in a new thread or what happens? Whether they actually run in parallel or sequential, this all depends on the thread pool size. With single thread pool, tasks queue up, next run waits. With multiple threads, tasks can overlap. Now, scheduled with fixed delay runs repeatedly with fixed delay between the completion of one execution and the start of the next. For example, a task starts at 9, initial delay is 10 minutes, first run at 9:10, task takes 20 minutes, so it finishes at 9:30 with 10-minute fixed delay. The next task runs at 9:40, 10 minutes after finishing the first task. No overlap. Each run waits for the previous one to finish. Moving on, the scheduled thread pool executor, the concrete scheduler. Scheduled thread pool executor is the concrete implementation of scheduled executor service. It extends threadpool executor class and adds scheduling capabilities. Internally, it uses a special work queue called delayed work queue that holds tasks ordered by their scheduled execution time. So here how you can create scheduled executor service. You can use schedule method to run a task, for example runs after 5 seconds, and scheduled at fixed rate to run a task maybe for every 2 seconds starting after 1 seconds. So here is the complete family tree. Executor interface, the root, just execute. Executor service, again interface, adds lifecycle and future support. Abstract executor service, abstract class, provides default implementation. ThreadPool Executor class, the general purpose ThreadPool engine. Scheduled executor service and interface adds scheduling, and scheduled ThreadPool Executor class combines scheduling with thread pooling. Understanding this hierarchy helps you choose the right type for your use case. Need simple async execution? Use executor. Need to manage shutdown, use executor service. Need full control over threads and queue, use threadpool executor. Need periodic tasks, use scheduled threadpool executor. Now let me introduce you to the lesser known but incredibly useful class, that is executor completion service. This is not an executor itself, but a helper that combines an executor with result queue. Imagine you submit 10 tasks to a thread pool. You want to process the results as they complete in the order they finish. The naive approach is to store all future objects, then loop through them, calling get method. But get method blocks. So if the first task takes the longest, you are stuck waiting even if later tasks finished earlier. So do you see the problem here? If the first task is slow, you wait. But tasks from 2 through 9 might have finished much earlier. You're wasting time. And here enters executor completion service. Executor completion service solves this problem. It wraps an executor and maintains a separate blocking queue of completed tasks. As soon as a task finishes, its future is placed in this queue. You can then take completed tasks in the order they finish. So we submit all the tasks and process the results as they complete. The completion service.take method blocks until any task completes, but the future.get will not block here because task is already done. Now that we understand the structure, let's look at the ready-made thread pools Java provides. These are the ones you'll use in your daily work. Each has its own personality, its own behavior, and its own risks. Let me introduce you to the executors class. This is not part of the inheritance tree. It's a utility class, like a factory that creates different types of executors for you. Think of it as a helper that saves you from writing boilerplate configuration code. The executors class provides static factory methods like newFixedThreadPool, newCachedThreadPool, newSingleThreadPoolExecutor, newScheduledThreadPool, newWorkStealingPool. And these all methods return pre-configured executor instances. These are the ones you'll use most often in your day-to-day coding. Let me walk you through each one of them. First, new fixed thread pool. This creates a pool with fixed number of threads. Let's say you set it to 10. So what happens? Initially, no threads. As tasks arrive, threads are created up to 10. Once you reach 10, the thread count stays constant. If thread dies due to an unexpected exception, a new one is created to maintain the pool size. The work queue, it's an unbounded linked blocking queue. That means tasks keep waiting if all threads are busy. So when to use this? When you have stable workload and you know exactly how many threads you need. But the catch here is the unbounded queue. If tasks arrive faster than they can be processed, the queue keeps growing and it can cause memory problem. Moving on, new cached thread pool. This is the extreme opposite. It creates threads on demand and reuses idle threads. If the thread is idle for 60 seconds, it gets removed. If new tasks arrive and no threads are available, it creates a new thread. There is no upper bound. Max pool size is nearly 2 billion, which is practically unbounded. The work queue is synchronous queue. This is special. It doesn't actually hold tasks. Each insert operation must wait for a corresponding remove operation. So when a task arrives, if thread is waiting, it takes it. Otherwise, a new thread is created. This pool can grow indefinitely, so use it only for short-lived tasks where you are sure the load won't spike. So new cache thread pool is suitable for IO tasks. IO bound tasks like network calls, file read writes, database query are often spend their time waiting. While one thread is blocked on IO, the pool can spin up more threads to keep throughput high. But here is the catch. Since there is no upper bound on the threads, under high load, it can create thousands of threads and crash with out of memory error. Next, new single thread executor. As name suggests, this creates a single worker thread. Tasks execute sequentially, one after another. If the thread dies unexpectedly, a new one is created to maintain the single thread guarantee. So when to use? When you need guaranteed sequential execution. When you want to ensure tasks don't run concurrently. The special feature of this is it provides memory consistency guarantees. Writes from one thread are visible to the subsequent threads. Moving on, next is new scheduled thread pool. When we write executors.newScheduledThreadPool with 5 core pool size, we are creating scheduled ThreadPool executor service instance backed by thread pool of 5 worker threads. This means up to 5 tasks can be scheduled and executed concurrently, whether they are one-time delayed tasks or periodic tasks. Unlike the regular thread pool executor, this class specializes in scheduling commands to run after a given delay or at a fixed intervals. It inherits all the flexibility of ThreadPool executor but adds scheduling capabilities. For queuing, scheduled ThreadPool executor uses special delay queue, delayed work queue. This queue holds tasks along with their scheduled execution times. Tasks don't just sit in, first out order. Instead, the queue ensures that the tasks are released to worker threads only when their delay has expired. This is what enables precise scheduling. But what if multiple tasks are due at the same time? Then these tasks are handled in order of submission. Unlike bounded queue in ThreadPool executor, this delay queue is unbounded, meaning tasks can keep piling up if you schedule too many tasks, though they'll only execute when their time comes. You'll notice here it sets the maximum pool size to integer.max value. At first, that seems like it could allow billions of threads, but in reality, this value is never used. Scheduled thread pool executor always runs with fixed number of threads equal to the core pool size you specify. The maximum pool size is just a placeholder required by a thread pool executor constructor. So why it doesn't grow beyond core size, you may ask? The answer lies in its design philosophy. By definition, scheduled thread pool executor is meant to be predictable. When you construct it with core pool size, that number is the only number of threads it will ever use. Allowing the pool threads to dynamically grow would break the guarantees of scheduled execution. For example, if tasks pile up, the executor doesn't create new threads to catch up. Instead, it ensures tasks run in order and at the right time, even if that means waiting. Moving on, next is new work stealing pool. It creates a special type of executor service that uses work stealing algorithm. Unlike fixed or cached thread pool, this pool is built on top of fork join framework. By default, it sets its parallelism level to the number of available processors, so it automatically adapts to the hardware. The idea behind work stealing is that each worker thread maintains its own queue of tasks. If one thread finishes its work early while others are still busy, it can steal tasks from another thread's queue. This reduces idle time and improves overall throughput, especially for divide and conquer style problems where tasks can be broken into smaller subtasks. Now, these factory methods are convenient, but interviewers don't ask about convenience, they ask about control. They want to know if you can build a thread pool from scratch with proper bounds and rejection handling. Let me show you how. Imagine this interview question. We have used all the factory methods. Now we need fine control. How would you construct a thread pool executor manually? So let me break down the constructor parameters that we need to build a thread pool. Core pool size, the minimum number of threads to keep alive even if they are idle. The max pool size, the maximum number of threads allowed. Keep alive time. If thread count exceeds the core pool size, idle threads wait this long before getting terminated. Work queue, the queue that holds tasks before execution. I used array blocking queue with capacity 100. This bounds the queue, preventing memory issues. Thread factory, the factory to use when the executor creates a new thread. Use this to name your threads like this. Set daemon status, assign thread groups maybe. Keep in mind that named threads save hours during debugging. At last, rejected execution handler. This controls what happens when a queue is full and all threads are busy and the new tasks cannot be added to a queue. I used caller runs policy, which means thread calling execute method runs the task itself. This provides back pressure. So let's understand the flow. Here is how ThreadPool Executor works internally. If current thread count is less than core pool size, create a new thread for a task. If core pool size is reached, queue the task. If the queue is full and thread count is less than maximum pool size, create a new thread. If the queue is full and the thread count is at maximum pool size, reject the task using the rejection handler. This flow is critical to understand because many developers think core pool threads fill up, then immediately max threads are created. That is wrong. The queue comes first because if core pool size is reached, queue the task. Now that we understand the producer consumer pattern, let me show you what actually happens inside those worker threads. This is the magic behind thread pools. Each worker thread in a thread pool runs a simple but powerful loop. It keeps running, trying to fetch tasks from a shared queue and executing them one by one. When there are no tasks, it waits until new task arrives. When the pool is shut down, it gracefully exits. Here is the simplified version of what a worker thread code looks like. This is not the exact ThreadPool executor code, but it captures the essence. See what's happening here. The worker thread has a reference to a shared task queue. Inside its run method, it enters a loop. Each iteration, it calls taskQueue.take method. Now take method is a blocking operation. If there is a task available in the queue, it returns immediately and the thread executes it. But if the queue is empty, the thread goes to waiting state right there, waiting for task to arrive. This is efficient. Idle threads don't consume CPU. Once a task is submitted to the queue by a producer, one of the waiting worker threads wakes up, grabs that task, and executes it. After finishing, it goes back to the queue for the next task. This loop continues until the pool is shut down. When we call shutdown method, we set flag and interrupt the thread. If the thread was waiting on a take method, it throws interrupted exception, which we catch it and break the loop, and the thread terminates. This design is incredibly efficient. Threads are created once and reused for thousands of tasks. No more creating and destroying threads for every request. No more overhead. Just a simple loop and a shared queue. In a real thread pool, you have multiple worker threads all running the same loop, all pulling tasks from same queue. The blocking queue handles all the coordination, ensuring each task is taken by exactly one thread and managing the waiting and waking up of threads. This is why thread pools scale so well. The number of threads is fixed or bounded, but the number of tasks they process can be enormous. The queue acts as a buffer, smoothing out bursts of incoming tasks. So, the key takeaway is a thread pool is just a collection of these worker threads, all sharing a work queue. The threads spend most of their time either executing tasks or waiting quietly for next task. This is the heart of Executor Framework. Now, let me show you a complete working custom thread pool that you can actually run. This will help you understand how everything fits together, the bounded queue, the worker threads, and the first in first out task processing. I have kept it simple so you can see the core ideas, no fancy optimizations, just the basics. Let me walk through it. Let me explain what's happening here. First, we create a linked blocking queue with fixed capacity. This queue holds tasks in, first out order, the order they were submitted. When the queue is full, any thread trying to submit a task will block until space becomes available. That's a back pressure. It prevents the system from being overwhelmed. The worker threads are simple. Each run a simple loop, repeatedly calling task queue.take. This method blocks if queue is empty, so idle threads just wait without consuming CPU. When task arrives, one worker thread wakes up, takes it, and executes it. After finishing, it goes back to the queue for the next task, as we have seen earlier. The shutdown mechanism is important. We set a flag shutdown and then interrupt all worker threads. In the workers run method, we check if the shutdown has been called and the queue is empty. Only then we exit. This ensures that any tasks already in queue are processed before the threads die. In the execute method, we use taskQueue.put method, which blocks if queue is full. This gives us bounded blocking queue, perfect for controlling resource usage. Now this is a simplified version. A real thread pool executor has many more features. Core or max pool sizing, keep alive times, rejection handlers, and many more. But this example captures the essence of how a thread pool works under the hood. Try running this code yourself. You'll see that these three worker threads processes 10 tasks and the queue handles the overflow. It's a great way to really understand what's going on. Let's quickly recap what we covered today. We started with the problem of raw threads, lifecycle overhead, memory pressure, and stability risks. Then we saw how the executor framework solves these with the producer consumer pattern and the execution policies. We walked through the inheritance hierarchy so you understand the structure. We looked at the predefined thread pools from the executor factory. And finally, we built a custom thread pool that you can use in interviews or the real projects. One last thing to remember, every thread you start encodes a trade off between responsiveness, complexity, and cost. So always design with the promises you can keep. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.